butadiene is dimerized at 350 degrees Celsius in the gas phase according to second-order kinetics. Data were taken at constant volume, time in minutes, and total pressure in Torr, starting with pure butadiene 2A to B. Determine the rate equation. We are given with temperature, which is 350 degrees Celsius. From the data given, we can see that the initial partial pressure of A and the total pressure at time 0 is 500 torr. Probably we'll also need a value for gas constant in terms of torr, since our pressure is in torr, which is 62.36 liters torr per Kelvin mole. The reaction is in second-order kinetics. We have a single and elementary reaction with the stoichiometric equation 2A to B. Now we are asked to determine the rate equation. As we can see, the data given is in total pressure, so we'll have the rate equation in terms of pressure. We know that for second-order kinetics, the rate equation is negative RA equals negative dCA over dt equals kCA squared. This is our equation 1. Converting this in terms of pressure, we'll use the DL gas equation, PV equals nRT. In terms of concentration, we just put this V down here and we'll have N over V, which is equal to Ca. So we have PA equals CART. Manipulating, we get RCA equals PA over RT. Now, we substitute this to our equation 1, which is this one. So we'll have negative D PA over RT all over dt equals K PA over RT squared. Since 1 over RT is just constant, we just put that here. Negative 1 over RT d PA over dt equals K PA squared over RT 180 squared. We can just cancel this, and this one we're just left with 1. So we'll have negative dPA over, we put this down here, PA squared equals K over RT dt. Now we integrate both sides. This from PA naught to PA, from 0 to T. Now we have negative PA to the negative 1 over negative 1, evaluated from PA naught to PA equals K over RT times T evaluated from 0 to T. Now we have our equation 2, which is 1 over PA minus 1 over PA naught equals K over RT times T. Our equation 2, which is the rate equation in terms of pressure. Now we need equation 5 of the book Chemical Reaction Engineering by Octave Levenspiel. I don't really know the correct pronunciation of the name, but anyway, we have PA equals PA naught minus A over delta N times pi minus pi naught. Now, substituting the given values to this equation, we have PA equals 500 minus A. A is just the number of moles for our reactant, which is 2. And delta N is the difference between the number of moles of our product and our reactant. So we have 1 minus 2, which is negative 1, times pi minus 500. So we have now our PA equals 500 plus 2 pi minus 1000. Our PA then becomes 2 pi minus 500. This is our equation 3. So substituting this equation to our second equation, which is 1 over PA minus 1 over PA naught equals K over RT times T, we have 1 over 2 pi minus 500 minus 1 over 500 equals K over RT times T. Now rearranging this to form a linear equation, we have 1 over 2 pi minus 500 equals K over RT times T plus 1 over 500. Now this is our y, our m, our x, and our y-intercept. So we just have to evaluate 1 over 2 pi minus 500 for the values of our y. Then we can graph x versus or time versus this. Actually, I've already calculated the values and tabulated it. This is it. So we have for time 0, our y is 1 over 500. That is 1 over 2 times 500, which is 1000, minus 500, this becomes 1 over 500, and so on. If you have a 991 ES Plus Cashew calculator, or any calculator that can solve for linear regression, you can use it. So now I just have to input my x, 0, 6, 12, 26, 38, 60. Our y is 1 over 500, 1 over 434, 1 over 384, 1 over 302, 1 over 256, and 1 over 200. Now solving for our r squared, we have 0.999859437. So our r squared is 0.99999. Solving for our m, which is K over RT, we have 4.999762522 times 10 to the negative 5. So m equals K over RT equals 4.9998 times 10 to the negative 5. Our RT is just 62.36 liter Torr per mole Kelvin multiplied by the temperature, which is 350 plus 273.15, that is Kelvin. Our RT then is equal to 38859.634 liter Torr per mole. Our m, by the way, is per minute because we have K over RT times T. T is in minute. So for dimensional analysis, we have to divide our slope also with time. So we have the unit per minute. So now we have to evaluate our K, which is 4.9998 times 10 to the negative 5 times 38859.634. So our K then is equal to 1.9429 liter Torr per mole minute. Now substituting our K to our equation 1, which is this. We now have negative RA equals negative dCA over dt equals KCA squared, or this is equal to negative 1 over RT times dPA over dt equals KPA squared over RT squared. Our negative RA then is equal to our K, which is 1.9429 liter Torr per mole minute times or divided by our RT, the square of our RT, which is 38859.634 liter Torr per mole times the pressure of A at any time T squared. So our negative RA then is equal to by the way, this is square. Our RT then is 1.2866. Our negative RA is 1.2866 times 10 to the negative 9. The unit is mole per liter Torr minute times PA squared. Or you can just write negative RA equals 1.2866 times 10 to the negative 9 PA squared. This is now our rate equation. This means that the rate of disappearance of A is this much multiplied by the square of the pressure of A at any time T. So if my pressure is, let's say, 300, so the square of my pressure times this much is the rate of disappearance of my A at that particular time. You can also write this in terms of total pressure because the given value is in total pressure. So we have negative RA equals 1.2866 times 10 to the negative 9 times 2 pi minus 500 squared. So that's it.